James Webb just released something incredible. Astronomers have just mapped nearly 800,000 galaxies within a single deep field survey. Some of them are so distant that their light began its journey over 13 billion years ago, when the universe was still in its infancy. For the first time, humanity has stitched together a map of the universe that spans almost all of cosmic history, using a telescope powerful enough to see galaxies as they existed just a few 100 million years after the Big Bang. Now, without wasting any more time, let's dive in. Scientists working on the COSMOS-Web project have released the largest, most detailed map of the universe ever assembled. Using the James Webb Space Telescope, the team spent 255 hours staring at a single patch of sky known as the cosmos field, a region deliberately chosen because it's unusually empty of nearby stars and dust. That patch covers just 0.54 square degrees of sky. That's roughly 3 times the apparent size of the moon. And inside that tiny sliver, nearly 800,000 galaxies. Some are relatively close to us. Others are so far away that their light started traveling more than 13 billion years ago, back when the universe was just getting started. We've had deep field images before. Hubble's ultra-deep field was revolutionary, but it showed only a few thousand galaxies, and it struggled to see the very earliest ones. Webb changes that. As the universe expands, light from the farthest galaxies gets stretched, shifting out of visible light and into infrared, which our eyes can't see. That's exactly what Webb was built for. Its 21-foot gold-coated mirror and ultra-cold instruments, operating near absolute zero at the Sun-Earth L2 point, are designed to catch photons that left their sources billions of years ago and have been fading ever since. COSMOS-Web isn't just deeper, it's broader. Instead of zooming in on a tiny pinprick, Webb mapped a wide region with enough depth to trace galaxy evolution across almost the entire age of the universe. When the COSMOS-Web team began analyzing the data, they ran into an immediate problem. There were far more galaxies in the early universe than existing models predicted. At certain distances, especially really far away, where the light has been stretched a lot, called redshift 7 and beyond, the Webb telescope is finding up to 10 times more galaxies than scientists expected. These aren't faint smudges, either. Many of them are surprisingly bright, unexpectedly massive, and show more structure than scientists thought galaxies that early in the universe should have. As Caitlin Casey, co-lead of the Cosmos project, put it, ever since JWST started sending back data, scientists have been asking, is this telescope revealing cracks in our current model of the universe? That's not a casual question. In standard cosmology, structure builds slowly. After the Big Bang, dark matter collapses first, gas falls into those halos, stars form galaxies, gradually assemble. The earliest galaxies were expected to be small, irregular, and short-lived. But Webb is finding galaxies that look too mature, too massive, too organized for their age. Some appear just 300 and 500 million years after the Big Bang, yet already contain billions of solar masses and stars. Heavy elements like nitrogen central black holes. That shouldn't be easy. And yet, it's happening everywhere Webb looks. Seeing almost all of time at once, one of the best things about the COSMOS-Web map is that it allows astronomers to do something they've never been able to do before. They can line up galaxies by cosmic age and watch structure emerge. In a single dataset, you can see nearby galaxies as they are today. Galaxies from 3, 4, 8, and even 10 billion years ago, and some of the earliest galaxies ever discovered, all at once. This turns the universe into a natural laboratory. Instead of guessing how galaxies evolved, scientists can compare different eras directly, and what they're seeing is not a smooth, gradual buildup. It's fast, violently fast. The time Webb is looking at is called the Cosmic Dawn, when the first stars lit up and brought an end to the universe's dark ages. Before that, the universe was filled with neutral hydrogen, with no stars, no galaxies, and no light. Then, Around 150-200 million years after the Big Bang, the first stars formed. These were likely population 3 stars, massive, short-lived, metal-free objects that quickly enriched the surrounding gas. Webb may be seeing their fingerprints. In COSMOS-Web and related surveys, astronomers have identified galaxies with extremely low metal content, unusual spectral signatures, star formation rates far higher than expected. Some candidates may be direct descendants of the very first stars. Galaxies aren't the only things forming too quickly. So are supermassive black holes. Webb has identified black holes with millions of solar masses less than 600 million years after the Big Bang. That's a problem. In theory, black holes grow by accretion, swallowing matter over time. But to reach that much mass so early in the universe's history, these objects would have to either start off incredibly large or grow by pulling in matter much faster than the Eddington limit, the point where the outward pressure from radiation equals the inward pull of gravity, normally putting a cap on how fast something can grow. Webb is seeing evidence for super Eddington accretion, black holes growing at rates once thought impossible. In some cases, the black hole appears to have formed before the galaxy around it. That flips the usual narrative on its head. One of the strangest discoveries enabled by COSMOS-Web is a population of compact, bright, red objects, nicknamed little red dots. They are extremely small, incredibly bright, and surprisingly common in the early universe. They don't behave like normal galaxies. Some may be. Ultra-dense star clusters, galaxies dominated by obscured black holes, precursors to quasars. Whatever they are, they were not expected, and they show up in large numbers. Again, the universe appears busier than predicted. So, did JWST change the size of the universe? No, and this is important. The age of the universe and the size of the observable universe are not suddenly in doubt. Those numbers come from a combination of sources: the cosmic microwave background, measurements of large-scale structures in the universe, and the predictions of general relativity. Webb has not overturned them. What it has done is expose the density of structure within that volume. The universe isn't emptier than we thought. It's fuller. When people say JWST discovered the true scale of the universe, what they're reacting to is this. In a patch of sky that looks empty to the naked eye, Webb reveals hundreds of thousands of galaxies. Stacked across time, it creates a visceral sense of scale, not in distance, but in abundance. The universe isn't just vast, it's packed, and that has consequences. Dense early galaxy populations feed directly into the formation of galaxy clusters, filaments, and superstructures. If galaxies formed earlier and faster, then the cosmic web may have taken shape sooner than expected. This ties into discoveries of enormous structures, from superclusters to candidate walls, that push the limits of cosmology. The COSMOS-Web map doesn't prove those structures exist, but it makes them less surprising. JWST doesn't deliver finished images. It delivers raw data, massive data sets that need advanced calibration, careful redshift estimation, detailed classification of galaxy shapes, and enormous computing power to process and analyze it all. The Cosmos collaboration spent 2 years turning that raw data into a usable map, and then released it publicly. That means amateur astronomers can explore the data, students can analyze it, and independent researchers can use it to test their own models, opening up discovery to a much wider community. This isn't a closed result, it's an open challenge. If you genuinely enjoy exploring the universe and its mysteries, consider subscribing. It helps us keep going. What this means for cosmology. COSMOS-Web doesn't say cosmology is wrong. It says it's incomplete. The models still hold up, but they might be missing some key pieces, like how efficiently stars formed in the early universe, how the first black holes were seeded, or how feedback processes worked in extremely dense environments. The universe may have been better at building complexity early on than we assumed. Think about this. From Earth, the cosmos field looks empty. From Webb's perspective, it contains nearly 1 million galaxies, each with billions of stars, stretching across almost the entire history of the universe. That's not a change in scale. That's a change in awareness. James Webb did not redefine the universe's size, but it may have redefined our expectations of what the universe was capable of, how quickly it could organize matter, how early it could build galaxies, and how densely packed cosmic history really is. If a tiny patch of sky can contain almost 1 million galaxies, what do you think we'll find when Webb maps even more of the universe? Tell me in the comments. See you in the next video.